I am Dr. Aloka Das, working as an associate professor in the Department of Mathematics of Jadavpur University. In this project, I am going to teach the course Partial Differential Equation. Now, what is the utility of this course? The study of differential equation had been started since the pioneer work by Newton in 16th century. That time he invented the laws of motion, and with the help of calculus he wrote down the equation of motions as ordinary differential equation. But to know or to study any phenomena in nature, we need both the time derivatives and the space derivatives. Subsequently, the study of partial derivatives and partial differential equations are developed. So, in this course, the entire course is divided into 10 chapters, and in the first chapter we shall discuss about the basic concepts of partial differential equation, and this chapter is also divided into 3 modules. In first module we shall discuss about the basic ideas and the definition of partial differential equation. Let me first define what is a partial differential equation. An equation involving 2 or more independent variables and one dependent variable and its all order derivatives is called a partial differential equation. Thus, the general form of a partial differential equation can be represented by equation number 1, where ux, uy, these are the partial derivatives with respect to x and y, and similarly we can define all other partial derivatives. Now, in equation number 2, we have shown some partial differential equations. So, these are the examples of partial differential equations. Now, we want to define order of a partial differential equation. The highest order derivative present in a partial differential equation is called the order of that differential equation. If you observe equation number 3, there are 2 equations. In the first equation, the highest order partial derivative is 2, and also in the second equation, the highest order derivative partial derivative is also 2. So, equation 3 gives the examples of second order partial differential equation. Now, if we observe equation number 4, the highest order partial derivatives present in this equation is 3. So, this is an example of a third order partial differential equation. Now, according to complexity in a partial differential equation, we can categorize a partial differential equation into 4 categories. The simplest one is the linear partial differential equation. A partial differential equation is said to be linear if it is linear in the unknown function and all its derivatives. One example of a linear differential equation is given in equation number 5. So, if you see the coefficients of the derivatives in this equation, they are only function of x and y. So, this is a linear differential equation. Now, we shall define a quasi-linear differential equation. A partial differential equation is said to be quasi-linear if it is linear in the highest order derivative of the unknown function. The coefficient of highest order term may be function of independent variables, dependent variables, and the lower order derivatives. One example of quasi-linear equation is KdV equation, which is written in equation number 6, and this is a third order quasi-linear differential equation, and this equation appears in plasma physics and in nonlinear dynamics. Now we shall define a semi-linear partial differential equation. A partial differential equation is said to be semi-linear if it is linear in the highest order derivative of the unknown function. But there is a difference between a quasi-linear and semi-linear differential equation. In case of a semi-linear differential equation, the coefficients of higher order derivatives are only function of independent variables. But in contrast, in case of quasi-linear equation, the coefficient of highest order derivatives may be function of dependent variables and the partial derivatives of lower order. One example of semi-linear equation is written in equation number 7, and another example is also given in equation number 8, where del square is the Laplacian and which is defined as del 2 del x square, del 2 del y square, del 2 del z square. The equation number 6 appears in differential geometry. And the most complicated equation which does not belong to the earlier categories, that means the equation which is neither linear nor quasi-linear or nor semi-linear, that equation is called a nonlinear equation. A nonlinear equation is very complex and very difficult to solve. This is one example of nonlinear equation, and there are many equations which are nonlinear. One of the famous equation is the Navier-Stokes equation, which appears in fluid dynamics, and that equation is not written here. So, nonlinear equation is a very complicated differential equation. Till now we have defined various type of partial differential equation according to the complexity, like linear differential equation, quasi-linear differential equation, semi-linear differential equation, and lastly nonlinear differential equation. Now we have to think about how these differential equations appear to solve any physical problem. To solve any physical problem with the partial differential equation, we have to consider some supplementary conditions, and those conditions are known as initial conditions or boundary conditions. In our next slide, we shall show how these conditions appear to solve any physical problem. Now we shall take one example. So, this is example of a physical system where the partial differential appears together with some supplementary condition. Consider a thin homogeneous perfectly flexible string which is under uniform tension along x axis in its equilibrium position, and the end of the string are fixed at x equals to 0 and x equals to L. Now, the string is pulled aside a short distance and then released. So, the string will now under free vibration. So, the motion of the string can be written by the differential equation del 2u del t square equals to c square del tu del x square, and this equation is known as wave equation. And there are some conditions, those are to be maintained to solve this problem. Those are initial conditions. So, initial conditions, which is the condition which is given at time t equals to 0. So, u x at 0 equals to f x, that means we are assuming the position of the string obeying some function f x, and the velocity of the string is given by the function g x. And we also have the boundary conditions u 0 t equals to 0 and u L t equals to 0, since the two ends of the string are fixed. So, the initial conditions and the boundary conditions are the supplementary conditions. So, we have to solve the partial differential equation together with these two conditions. Now, if the problem is in unbounded medium, then we cannot define any boundary conditions, then the equation is to be solved together with the initial condition. So, that type of problems are called initial value problem or Cauchy problem. So, this is one example of initial value problem. This is heat equation, one dimensional heat equation, and the supplemented condition is given by u x 0 equals to f x. So, this is the initial temperature field. So, according to the supplementary condition, we can divide a problem or a mathematical problem into some categories like initial value problem, boundary value problem, or mixed initial boundary value problem. Before solving a partial differential equation, we have to think about the solvability of the partial differential equation. A mathematical problem is said to be well posed if it satisfies the following three conditions. The first one is the existence, which says that there is at least one solution of the problem, and the second one is the uniqueness, which says that there is at most one solution, and the third important criteria is the continuity, that is the solution depends continuously on the data. So, a mathematical problem is said to be well posed if it satisfies all three conditions. So, it is possible to find a solution of a well posed problem. A problem which is not well posed, that means which does not satisfy any of the above three conditions, is called an ill posed problem. An ill posed problem cannot be solved mathematically. Now, we shall derive equation of a surface and equation of a curve in 3 dimension, and we shall also show that how partial derivatives appears to find direction of a tangent to a given curve and direction of the normal to a given surface. The concept of this module will help us to further development of the subject PDE or partial differential equation. First, we shall discuss about equation of a surface in 3 dimensional space. Let x, y, z be the coordinates of a point P refer to a 3 dimensional Cartesian system of axes, and coordinates are connected by a relation of the form given in equation 10. So, this is the general form of the equation of a surface capital F x y z equals to 0. Now, from this equation one can write z as function of x and y. So, this is another form of representing equation of a surface, and there is one well known form which is called the parametric representation of a surface is given in equation number 11. In this equation, the coordinate x is written as function of two parameters u and v, and y is also written as function of two variables or two parameters u, v, and z is also function of two parameters u, v, and this representation is the parametric representation of the surface. Now, we propose that the equation 10 and equation 11 are equivalent. To show that, So, let us first take the parametric form of the surface. So, from the first two equation, that means x equals to f1 uv and y is equal to f2 uv, we can solve for u and v such that u is some function of x and y and v is another function of x and y. Now, if we substitute the values of u and v in the third equation, that is z equals to f3 uv, that will give a relation in the form z equals to fxy, and this is nothing but the form 10. Therefore, the equation of surface which is given in 10 and given in 11 are equivalent. But we have to remember that the parametric representation of a surface is not unique. That means the equation of a surface can be represented in many different parametric representation ways. So, let us take one example. So, this x equals to a sin u cos v, y equals to b sin u sin v, z equals to c cos u. This is parametric representation of the surface which is written below. This is actually a ellipsoidal surface which is x square by a square plus y square by b square plus z square by c square equals to 1. And this equation is obtained by eliminating the parameters u and v from the three equations. And now, if we look at the second representation, parametric representation of the surface. So, from the second equation, that means x equals to 2av by 1 plus v square sin u, y equals to 2bv by 1 plus v square cos u, and z equals to c into 1 plus v square by 1 plus v square. So, from these three equations, if we eliminate u and v, we will get the same surface, the same ellipsoidal surface which is written below. Thus, the parametric representation of the ellipsoid may be of two different forms. So, parametric representation of a surface is not unique. Now, we shall go discuss how can we represent equation of a curve. Suppose there is a point with coordinates x, y and z and which satisfies equation number 10. That means the point x, y, z lies on the surface capital F x, y, z equals to 0. Now, consider the plane z equals to k, where k is a constant. So, this equation of the surface and z equals to k, that means we are considering the points where this surface and the plane z equals to k intersect, and those intersecting points will give a curve. Therefore, the equation of a surface and equation of a plane together represent equation of a curve. Now, let us take one example. This is equation of an elliptic paraboloid. So, its equation is x square by a square plus y square by b square equals to 2z by c, where c is a constant. Then, the section of the elliptic paraboloid by the plane z equals to k, that means we are cutting, this is the surface elliptic paraboloid. Now, let us cut this surface by the plane z equals to k. then that will give an ellipse. So in this equation, if this is also satisfied, means if we cut it by z equals to k, that means if in this equation if we put z equals to k, then this equation will give equation of an ellipse. Therefore, this surface and the plane z equals to k represent a curve, and you can note that the center of this ellipse or the system of ellipse has the point at 0, 0 k, where k is positive and k is the parameter, and that can be visualized from this figure also. So, k is the parameter at which height you are cutting the surface by the plane. Thus, the whole surface of E is generated by ellipses like 13 with centers on the z axis, and k also varies. Therefore, we see that the equation of a surface and equation of a plane together represent equation of a curve, but in general, instead of a plane, if we cut a surface by another surface, then their intersection always gives a curve. Therefore, a curve may be thought of the intersection of two surfaces, and this is the general representation of the equation of a curve S1 f1 xyz equals to 0, and this is another surface S2 f2 xyz equals to 0. Like the equation of a surface, a curve may be represented in parametric form. The parametric representation of a curve is like this, where all the x, y and z coordinates are written as function of a parameter t, and t is a continuous variable. Now, the question is, how can we say that the equation 14 represent equation of a curve? That means we want to show that the equation 1, equation A, this representation and the parametric representations are equivalent. Now, from this parametric representation which is written in equation number 14, we can eliminate t from the first two equations to get a functional relation between x, y. Let us say that relation is phi 1 x y equals to 0, and similarly eliminating t from the first and the third equation will give a relation between x and z, and let that relation is phi 2 xz equals to 0. Now, this equation phi 1 xy equals to 0 represent equation of a surface in 3 dimension, that we already know, and phi 2 xz, these also represent equation of a surface in 3D. Therefore, equation of surface, two equations of surface together represent equation of a curve. Therefore, the equation of a curve which is given in form A or form B are equivalent. Now, we want to develop some geometrical idea from the equation of curves and equation of surface. First of all, we want to find direction cosines of the tangent to a given curve. Let the equation of a curve is given by x some function of parameter s and y is some function of parameter s and z is some function of parameter s. So, here s is our parameter and in this case s is taken as the arc length which is measured from a fixed point P0 along the curve. And let us take another point Q in the neighborhood of the point which has coordinates x, y and z. Therefore, we can write the coordinates of Q in this form as Q x s plus delta s, y s plus delta s and z s plus delta s. So that the arc length PQ is delta s and the chord PQ is delta L. So, if you see the picture, this is the point P whose coordinates are x, y, z with parameter value s, and Q is a point neighboring to the point P, and this is the point corresponding to the parameter value s plus delta s, and this is the chord PQ and this is the arc PQ. So, arc PQ is delta s and chord PQ is delta L. Now, when delta s tends to 0, this PQ becomes tangent to the curve at the point P, and also as delta s tends to 0, the chord length and the arc length, their ratio becomes 1. Now, think about the direction cosines of the chord PQ. Since the Q has the coordinates x, y, z with parameter values s plus delta s and P has coordinates with parameter values s, now the direction cosines of the chord PQ can be written in this form. And in this expression, if we expand x, y and z in Taylor series about xx, that will give this expression. Now, if we do this, we divide by delta s and here multiply with delta s, then there is terms of order delta s and these are the terms order delta s and these are the terms order delta s. If you take the limit as delta s tends to 0, these terms become 0 and this becomes 1 using this relation, and therefore, direction cosines converges to the values delta s by delta s, delta y by delta s, delta z by delta s. That means, if Q goes to P, the del dx ds, dy ds, dz ds represent the direction cosines of the tangent to a given curve at P x y z. So, we learned that if the equation of a curve is given in parametric form, which is written in equation number 15, the partial derivatives, this dx ds, dy ds, these are not partial derivatives, these are the ordinary derivatives because a is only parameter, this is a function of s. So, dx ds, dy ds and dz ds represent equation direction cosines of the tangent to the curve 15 at x, y, z. Suppose the equation of a curve gamma is given in parametric form, which is written here x as function of s, y as function of s and z as function of s. Let us suppose there is a curve gamma which lies entirely on a surface which is given here if x, y, z equals to 0. We also assume that the equation of the curve gamma is given in parametric form, which is written in equation number 15. Since the curve gamma lies entirely on the surface S, which is represented by this equation, will satisfy this equation. That means the coordinates of any point in the curve gamma will satisfy the equation of the surface. So, capital F xs, y xs, z xs, zs equals to 0. Since gamma lies entirely on surface S, so this equation will satisfy for all values of S. Now, taking derivative with respect to S, we get relation 17. So, in this equation we can observe that dx ds, dy ds, dz ds represent direction cosines or ratios of the tangent to the curve gamma at the point xyz. Therefore, del f del x, del f del y, del f del z represent equation or direction ratios of a straight line which is perpendicular to the tangent to the given curve gamma at xyz. Now, consider any curve which passes through x and which also lies on the surface S, then for that curve the equation like 17 will also hold. Therefore, this del f del x, the straight line having direction ratios del f del x, del f del y, del f del z represent the direction ratios of the normal to the tangent plane to the surface, or in other words del f del x, del f del y, del f del z represent direction cosines of the normal to a given surface. Thus, in module 1 of chapter 1, we got some basic ideas of partial differential equation. First of all, we have defined the various type of partial differential equations. Then we gave some examples of physical problems where these type of equations may arise, and finally we have shown how partial differential equation, or rather we can say that how partial derivatives can appear to solve some geometrical problem. Thus, in this way we end the module 1 of chapter 1.